Alright, let's keep it going. So now we are going to look at exactly what probability is. And now that we've framed the sorts of questions, the sorts of observations that we're trying to look for, now we can start talking about concretely what the probability, what the chance, what percent of the time things are going to happen. So a basic definition of probability is it's going to be the frequency uh, that an event occurs when performing an experiment, making an observation, whatever. We observe some sort of phenomenon, and it's the frequency that we expect it to happen. When I say frequency, I really mean the percent of the time that it happens, how often it happens. So then we have a definition. So the probability of a simple event E, which is denoted by P of E, put a P and then inside parentheses E, is a number that's between 0 and 1. Oops. And also, and these, if the sample space is equal to E1, E2, E3, all the way up through, say, E sub n, then if I take E1 plus E2 plus all the way out to En, if I add up all the probabilities, I get 1. If I add the probabilities of all the events in the sample space, I get 1. So what exactly do these mean? Well, first of all, why do we do a probability as something between 0 and 1? Here we're thinking of a percent as a decimal between 0 and 1. So, recall that I can start with any percent. If I have a percent, if I start with 80%, that corresponds to 80 divided by 100 is equal to 0.8. Whereas if I have, say, 0.25, that corresponds to 0.25 times 100%, which is 25%. So we're thinking of the percentage as a decimal, and although percent is a nice intuitive thing to work with, we prefer decimals because it actually makes arithmetic with probability easier. Now this then means that the sum of the probabilities is 100%. So the reason that the sum of the probabilities is 100% is one of the events has to happen. If I had the sum of probabilities of the events adding up to less than 1, that would mean that I was missing a possible event. Something that could possibly happen. Because, then, basically if the sum was less than 100%, I'd be saying that these things happen, 70% of the time. But what happens the rest of the 30% of the time? So that's why it has to add to 1, because we're really looking for a sample space to contain all of the possible things that can happen. Okay. Now let's make a note. We make reasonable, excuse me, let me go back. This is called an acceptable probability assignment. Our mathematical theory doesn't tell us, given some sort of experiment and a bunch of events, what the probabilities are supposed to be. All we can say is, just looking at the numbers, does this make sense as a set of probabilities? Yes or no? If it satisfies these conditions, that the probabilities are between 0 and 1, and that the probabilities add up to 1, then yes, this is an acceptable probability assignment. Now let's also note something, that how do we actually get probabilities? There are two basic ways. We can make assumptions, sort of mathematical assumptions, about the experiment or the outcomes, and this I will call theoretical, or we can collect data, which would be called empirical. Okay, so this is what we can do sort of mathematically or using sort of assumptions about how the world works. Empirical would be something like, polling. I find out how many people like Pepsi by polling them. Okay. Now, these, probability assignments obtained through these means are reasonable. They make sense, either because we've made some assumptions that make sense to us intuitively, we've collected data, and that's what the data says. So let's look at an example. We're flipping, we flip a coin, it lands on one side, the heads or tails, so our sample space is just S's, H, and T. So a theoretically reasonable assignment of probabilities is pH is equal to 0.5 and P of T is also equal to 0.5. Why is this acceptable? Because the probabilities are between 0 and 1, and the sum of the probabilities is 1. And reasonable, why is it reasonable? Well, we're just saying that it makes sense that heads and tails should come up the same percent of the time. Each should come up 50% of the time. That's just seems to make sense. B, an empirically reasonable assignment would come from flipping the coin, let's say 1,000 times, and then letting P of H be the percent of times heads came up, P of T the percent of times tails came up. So, for example, let's say H came up 520 times, and that would mean that tails had to come up 480 times. So we would then say that the probability of H would be 0.52 because it came up 52% of the time, and the probability of tails would then be 0.48. This is actually acceptable because these numbers 0.48, 0.52 are actually less than 1, and the sum of 0.48 and 0.52 is 1. So they are acceptable. And reasonable, we collected, we got these numbers from data. It's reasonable because we actually performed the experiment in real life and got our probabilities from that. So that is reasonable. What about some unacceptable, well, how about an unreasonable assignment? P of H is 1, P of T is 0. This means heads always comes up. I don't know about you, but I've never had a coin where heads always comes up. I suppose there are some gag coins out there which have heads on both sides, so heads always comes up. But no, this doesn't make sense. This is contrary to our real-world experiences. How about an unacceptable assignment? Let's say P of H is equal to 0.4 and P of T is equal to 0.4. While the numbers are between 0 and 1, the sum of the probabilities is 0.8, which is less than 1. So that's no good. That would mean that there was some other outcome, like the coin landing on its side, although I don't expect that. Another unacceptable assignment would be something like P of H is equal to negative 0.5 and P of T is equal to 1.5. Even though the sum of these two numbers is 1, negative 0.5 is less than 0 and 1.5 is greater than 1, and that is not allowed. So that is not acceptable. It doesn't make some sense for something to happen negative 50% of the time or 150% of the time. I don't even know what that means. Okay. Now, let's define some more things. The probability of, we're going to define the probability of an event. We're going to define the probability of a compound event E is denoted by PV and is given by, first of all, if it's just a simple event, it's just that event, the probability of that event. If it is the empty set, the probability is 0. If we have the whole sample space, the probability is 1. And for any other event, it's the sum of the probabilities of E, where E are the simple events in E. Okay, so if I have, so if E is an event that consists of a bunch of simple events, I just add the probabilities of those guys together. Great, there we go. So, for example, let's do some examples. Let's flip a coin twice, assign reasonable probabilities. So first let's do that. So what are the possibilities here? You could get heads, 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 tails, tails, heads, and tails, tails. We already talked about that. What would be reasonable here? Well, we might expect all possibilities to come up the same percent of the time. It should be completely random. So we have four events, and we expect same probability. So each probability has to be 1/4, which is 0.25. We'll talk about that in a bit. So the probability of heads, heads is the probability of heads, tails, is the probability of tails, heads, is the probability of tails, tails are all 0.25, and just check that this is acceptable. The only thing you really need to check is that the sum of these four numbers actually is 1. It's also reasonable because it's what we expect. Now let's do some probabilities. What's the probability that there is exactly one head? This is sort of lazy set builder notation. I'm not actually writing down the event explicitly. I'm just writing down the event, as a statement. Well, this is equal to, what is this set? It's heads, 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 tails, tails, heads. So it's equal to the probability of heads, heads, plus the probability of heads, tails, plus the probability of tails, heads, which is 0.25 plus 0.25 plus 0.25, which is 0.75. So we expect let me change this to at least one head. At least one head. And that should happen 75% of the time. B, do this as an exercise on your own. What's the probability of exactly one head? Okay. Oh wait,